Hello, my name is Qiqi Wang. Today I'm going to review a paper in Physics Today called 50 Years of Chaos. So this is a paper published by Edward Motter and David Campbell. So it turns out this year, 2013, is a 50-year anniversary of chaos. So in 1963, actually here at MIT, a meteorologist, Edward Lorenz, was the first one to discover a strange phenomenon later called chaos. So scroll down the paper. So this is Edward Lorenz over here doing research. And what he discovered is something that turns out to be very general in dynamical systems that describes a lot of the physical processes we encounter every day. What he discovered is that if he simulates a dynamical system with even very small difference in the initial condition, like what you see over here, the small difference in initial condition is going to evolve and become larger and larger until the two simulations becomes completely different. Okay, so he called this the butterfly effect, and he made a very interesting analogy. Like a butterfly flapping its wing in Brazil is going to cause a hurricane in Texas a few months later. And what is amazing is not only this interesting phenomenon that happens in his study, but actually how general the phenomenon is. And later on, actually 10 years later, people have discovered that a lot of different dynamical systems have similar behavior. And this is the later part of this paper, talking about not only the discovery of chaos, what kind of a system was studied when it was discovered, but also later on, like how people are able to use the results to study a lot of different dynamical systems. Some examples are given here. There are three pictures representing three completely different things that are amazingly can be described by the same phenomenon, that is chaos. So one is the rings of Saturn. How the rings are spaced is influenced by chaotic dynamics interaction between Saturn and its moons. And in B, this is the flow in the ocean, and visualized basically by plankton booms. You can see really the chaotic motion of the water in the ocean. And in C, it is a simulation of Earth's magnetic field. And it turns out Earth's magnetic field is going to flip its polar at random times. Well, not really random, because the process is determined by chaos, which by itself is deterministic, but the result is chaotic and seemingly random. So this is a very interesting paper that if you're interested in the history and recent developments of the field of dynamical system and chaotic dynamical systems, you should take a look. And what I want to say more is that right now, as we are simulating a lot of very interesting dynamical systems, and as our simulation becomes higher fidelity, we are more and more resolving a lot of the chaotic features of the natural world we are not resolving before. Some of the examples including fluid flows in aerospace engineering. Other examples, like in molecular dynamics, when people simulate how molecules interact with each other, they are simulating a chaotic dynamical system. There are other examples, like a lot of the simulation involves biology and parts of the human body, and they turns out to be also involving chaotic dynamics. So it is a very interesting subject, and now exactly 50 years old.